Modern physics rests firmly on the double foundation of quantum theory and the theory of relativity. Each grew out of a problem in classical physics, and each was born in the early years of the 20th century. Interestingly, light, or more broadly electromagnetic radiation, was involved in the birth of each theory. In each case, it was the explanation of the unexpected behavior of electromagnetic radiation that would end up challenging some basic concepts in classical physics. Yet for all the apparent similarities, the two theories stand in odd contrast. Relativity was essentially the product of one man, Albert Einstein. It was published in two chunks, each one a conceptually mature unit that hung together as a whole. The special theory, published in 1905, challenged concepts of space and time and tied them together to form a four-dimensional space-time continuum. The general theory, published in 1915, contained a new interpretation of gravity as a warp in the shape of space. Quantum theory, on the other hand, was the product of many minds. It was destined to evolve slowly, in fits and starts, over a period of about 30 years before finally growing into a coherent whole. Eventually, it would prove to be even stranger than relativity. Quantum theory was born as an inspired guess. It was meant to solve a difficult problem in something called black body radiation, not to create a new understanding of the physical world. The inspired guess was the quantum hypothesis, the assumption that luminous energy is released in distinct quanta which are equal to the frequency of the light, nu, times the constant, h. Max Planck was the man who made that guess, and the constant, h, is known as Planck's constant. But Planck took the position that these quanta had to do with the mechanism of emission, not with the nature of light. In 1905, Einstein took Planck's quantum hypothesis and used it to explain another problem in physics, the photoelectric effect. Niels Bohr was responsible for the next step in developing quantum theory. In 1913, he applied the concept of quanta to the atom. In the Bohr atomic model, the electrons were confined to certain specific orbits. The radii of these quantum orbits were determined by Planck's constant, h. Almost immediately, Arnold Sommerfeld further developed the model by applying Bohr's idea to elliptical orbits. The theory had to wait for about 10 years for the next significant development. In the meantime, things remained in a state of growing confusion. Consider, before the photoelectric effect had been explained by Einstein, it was believed, on the basis of solid evidence, that light was a wave. Now, starting with the equation for momentum, P equals mv, the relativistic expression E equals mc squared, the relationship V equals lambda nu between the velocity v of a wave, its wavelength, lambda, and its frequency, nu, and the quantum hypothesis, E equals h nu, an equation relating the momentum of a photon to its wavelength can be derived. Specifically, the momentum p of a photon equals Planck's constant, h, divided by the wavelength, lambda. In 1923, Arthur Compton demonstrated that this equation actually means something. That is, it is possible to speak of the momentum of a photon. Compton showed that in a collision between an electron and a photon, momentum, p, is conserved by a change in the wavelength, lambda, of the photon. The Bohr-Sommerfeld model of the atom, meanwhile, was based on the proposition that electrons could only occupy certain specific orbits, called quantum orbits, around the atomic nucleus. Bohr had derived an equation containing Planck's constant, h, that gave the value for the radius, r, of the permissible orbits. But while the Bohr-Sommerfeld model predicted some things very well, like the emission spectrum of the hydrogen atom, and while it helped explain the periodic table, certainly an impressive feat in itself, there were problems with it, things the theory either did not predict or that it predicted incorrectly. Also, the Bohr model didn't show why the electron should be confined only to particular orbits. That problem was tackled by Louis Victor Duc de Broglie, who was responsible for the next step in developing quantum theory. He reasoned that if light, which had been thought of as a wave, could have particle properties, then perhaps the electron, which was thought of as a particle, might have wave properties. Consider, Compton had shown that the momentum p of a photon equals Planck's constant, h, divided by the wavelength, lambda. De Broglie suggested that the same formula could apply to an electron. Thus, the wavelength, lambda, of an electron would equal Planck's constant, h, divided by the momentum, p. Since momentum equals mass times velocity, the wavelength lambda of an electron would, according to de Broglie, equal Planck's constant, h, divided by the electron's mass, m, times its velocity, v. With this concept, de Broglie could explain Bohr's quantum orbits as those orbits in which an electron wave could fit a whole number of times. In any other orbit but the ones permitted by Bohr's formula, the wavelength would not fit a whole number of times. As a result, it would interfere with itself destructively. Now, Bohr's formula for the radii of the permissible quantum orbits in an atom can be manipulated to read differently. So it becomes quite clear that de Broglie's concept is mathematically equivalent to Bohr's in describing the permissible quantum orbits. Yet it adds something. It gives a reason why the electron should be confined only to specific orbits. Still, the concept that a particle could have wave properties was, at the very least, difficult to believe. What were these waves? Did they represent a physical reality? What? De Broglie called them pilot waves, or matter waves, and thought of them as accompanying an electron in its orbit about a nucleus. Today, they are usually called de Broglie waves. But if these apparently unlikely waves really do accompany an electron in its orbit about a nucleus, they also ought to accompany an electron moving freely in space. And if that is so, there should be a way to verify them experimentally. Consider, from the formula lambda equals h over mv, we can calculate the de Broglie wavelength for an electron moving at, say, 10 to the 6th meters per second, a speed easily attainable in laboratory experiments. Interestingly, the wavelength comes out to about 10 to the minus 10th meters, about the same wavelength as X-rays. Now, X-rays, like visible light, are a form of electromagnetic radiation, but they have such short wavelengths that it is somewhat more difficult to demonstrate their wave properties. It is, however, possible. The atoms in crystals are arranged in orderly layers. Conveniently, these layers are about 10 to the minus 10th meters apart, just about the same length as the wavelength of X-rays. Consider what happens if a beam of X-rays is directed at the surface of a crystal. Part of the beam is reflected from each layer of atoms as it passes through the crystal. A photographic plate will detect and record these reflected X-rays. The final result, known as a diffraction pattern, is produced by the constructive and destructive interference of the reflected X-rays with each other. The diffraction patterns of X-rays had first been demonstrated in 1912. About a dozen years before, de Broglie suggested that there was a mysterious matter wave associated with electrons. Now, if this matter wave actually existed, and if it really had about the same wavelength as X-rays, then a beam of electrons directed at a crystal target should also show a diffraction pattern. Curiously, at about this time, the American physicist Clinton Davison, who had not heard of de Broglie's matter waves, tripped over precisely this phenomenon while performing an unrelated experiment. In trying to explain what appeared to him as some very odd results, he consulted with colleagues and was finally introduced to de Broglie's idea. With the theory in hand, he went back to the laboratory to test the formula against experiment and succeeded in verifying de Broglie's concept. Incredibly, de Broglie was right. Not only did the electrons show a diffraction pattern, but the measured wavelength determined from the spacing of the light and dark bands was exactly that predicted by the de Broglie formula for electrons traveling at any particular velocity. By 1930, similar experiments had been tried with atoms and with molecules. Once again, the diffraction pattern showed up, and once again, they matched the prediction. Before any of these experimental confirmations, however, the theory was developed even further. De Broglie's work was done for a doctoral thesis. It was radical enough an idea that it would have been easy to ignore for quite some time, particularly since it did not come from a physicist with an established reputation. Albert Einstein, however, was one of the people who did see de Broglie's work. Shortly after, he published a paper which called attention to the idea and supported it. Erwin Schrödinger read that paper, learned of de Broglie's work, and went on to develop wave mechanics. Almost simultaneously with Schrödinger's paper, Werner Heisenberg published a paper dealing with the same subject. But Heisenberg's paper started with different assumptions, used a different form of mathematics, and appeared to be totally unrelated to Schrödinger's work. Strangely, both of these papers seemed correct. That is, they both gave correct predictions. Soon after, Schrödinger showed that his wave mechanics and Heisenberg's matrix mechanics were really the same thing, and that one could be derived from the other. Thus, in 1925 and 26, quantum mechanics was born. It would quickly be developed to what is essentially its present level of understanding. But first, there was the problem of deciding just what Schrödinger's wave mechanics and Heisenberg's matrix mechanics meant.